Welcome to AP Chemistry at Hunting High School. I'm Brian Brown, and today we'll be looking at section 6.4 to 6.7 of chapter 6. And we left off yesterday looking at how classic physics said matter behaved like particles, energy behaved like waves, and scientists started to see instances where we were dealing with obviously light, which is supposed to be like a wave, but treating it like a particle helped us explain what was going on. Well, that was really thinking outside the box. And what eventually happened when we got to the Bohr model, it fell apart. Worked great for one electron, but anything past that in the mathematics started to fall apart. So while there was a kernel of truth in Bohr's model, there had to be more going on than we understood at the time. And it was a huge hurdle for scientists to overcome. And what really happened was when scientists, and this was really de Broglie, Louis de Broglie kind of turned the tables and he said, well, wait, scientists are treating energy like it's a particle. What would happen if we treated particles like it was a wave? And that really allowed us to get a better understanding of the electron and eventually allowed us to understand the electron better than we did with the Bohr model. So de Broglie proposed that if light can have material properties, particle properties, then matter should be able to exhibit wave-like properties as well. And he demonstrated that the relationship between mass and wavelength was given by this equation. The wavelength of an object was equal to Planck's constant over the mass times the velocity. And with this equation, then you could calculate basically the wavelength of a moving object. You just had to know its mass, its velocity, and you could calculate the wavelength. Well, what he was doing was he was treating particles like they were waves. So he was flipping the table once again in classic physics. And what he found out was large objects, everyday objects, honestly, the wave-like particles are so incredibly irrelevant that it just doesn't do any use to look at things in this way. But the smaller the particle is, the less important its particle properties become, and the more important its wave-like properties become. And an electron really is a very, very, very small particle. So he started the idea of thinking of electrons, which are particles, as if it was like an energy form. Now, around the same time frame, that we were really undergoing a lot of changes in thought in fundamental physics and chemistry. Another person came out of the picture, and what scientists were doing is they were getting very excited. They thought they had the secret to finding the two things we wanted to know about the electron. Where does it live? What's its location? And what's its energy? We felt those two things were just around the corner. With the advent of Bohr's idea, and along came de Broglie, we were getting closer and closer and closer to maybe understanding those two fundamental things. Well, at this same time frame, along comes a man named Heisenburg. And Heisenberg basically showed that what we were looking for, the holy grail of chemistry, finding the location and the energy of the electron, was impossible to know. And this really set scientists back for a while. They wasted a lot of energy trying to disprove his ideas here, but in the end, his ideas were proven true. And it was only by once again thinking outside the box that we were able to overcome his dilemma. So he basically showed mathematically that you can't precisely know both the position and the momentum slash energy slash velocity of a particle at the same time. And that's exactly what we were looking at with the electron. What was its position and what was its momentum slash energy slash velocity? And what Heisenberg said was, you're looking for something you can't know. Now, the change in x, that would be the uncertainty of position, is going to equal the change in mv, and that would deal with the uncertainty of momentum. And what he showed was that those two things multiplied had to be greater than or equal to h over 4 pi. Now, if we arrange this equation a little bit, we came up with this expression. The uncertainty of position is going to equal Planck's constant over 4 times pi times mass times the change in velocity. So in many cases, the uncertainty of the whereabouts of the electron is actually greater than the size of the atom itself. So if we look at knowing very specific information about the energy slash momentum slash whatever, so I'm just going to simplify it and say if we know very precise location about the energy, that means we're going to have a very, very, very low uncertainty, excuse me, in energy. And since that is on the bottom, the smaller this number gets down here, the greater this is going to become. So fundamentally, the better we know the energy of the electron, the less we're sure about its position. And where we were at in trying to find out and describe very specifically the energy of the electron, that was such a small uncertainty that if you actually looked at what this mathematics would say about the uncertainty of position, it was actually greater than the area of the atom itself. So fundamentally, with as specific as we knew the energy of the electron, that meant we had such a great uncertainty, we couldn't even be able to say that the electron was actually inside the atom anymore. And the problem was his mathematics are true. His mathematics hold up even today. The better we know the energy, the worse we're going to know the position. So if we get too specific with energy, we have a very big uncertainty with position. The better we know the position, the worse we know, or the greater the uncertainty of the energy is. And really, scientists wasted a long time trying to refute this, when in the end, they couldn't. But Schrodinger developed a way to get around it. And what he fundamentally said was, all we really need to know is where the electron is at most of the time. Not 100% of the time, but most of the time. So we can live with a little bit of uncertainty with position if it gives us better mathematical uncertainty and smaller uncertainty of the energy of the electron. And through his wave mechanics, which really started with the Broglie's idea, he was able to come up with a way for us to look at what the energy of an electron was with a little bit of uncertainty and a little bit bigger uncertainty about position. So realistically, all we really need to know is where's the electron at 90% of the time. So Schrodinger was the one who got around Heisenberg's problem. With his mathematical treatment for wave mechanics, basically we were looking at the dual wave particle nature of the electron, and we were incorporating both ideas to explain the energy and position of the electron. And this was really the beginning of modern quantum mechanics. It was treating particles like waves and treating energy like particles. And when we put that together, yes, under certain situations, materials behave like particles. That's most of the time. Under certain situations, energy behaves like a wave, and that's most of the time. But when you're dealing with very, very, very small particles, while it is a particle and it has particle properties, it also has very um, important wave-like properties. And we can use those two things to look at both position and energy of an electron. No, we're not going to know both of them specifically, but we can deal with the uncertainties involved in both. Now, the square of his wave equation actually gives us what's called the probability density, which is what you're looking at here. This is the probability of finding an electron in what we call our 1s orbital. So this is where this electron lives. This is like a snapshot taken second after second after section and then superimposed on top of each other. And what you get then is a probability density of where our electron lives. Where it's very dark here in the middle, you have a very high probability of having an electron. Where it becomes very diffuse here on the outside, you have a very low probability of finding the electron. So electron density, which is often called the electron cloud, is another way of expressing the probability density. So it's a way of looking at where the electron lives most of the time. And we don't really care where it's at all of the time. What we do is we draw basically a region of space where we're going to say with confidence that the electron is at 90% of the time. So solving the waves equation gives us a set of wave functions or orbitals. And orbitals basically describe the general location of electrons at specific energies. And when I say specific, I don't mean exact. I mean within relatively small uncertainty what our energy is. And then we have to live with the fact that we're going to have a larger uncertainty of position. But we don't really need to know where it's at all the time. We just need to know where it's at 90% of the time. So each orbital describes a 3D region of space where the electron is at 90% of the time. Now, an orbital is described by a set of quantum numbers, three fundamental quantum numbers. In the end, there's going to be a fourth quantum number we'll get at, but by and large, where our electron is at is described using three quantum numbers. Now, this is new, and this is something that was not in pre-AP chemistry. We may have talked about the principal quantum number and discussed quantum numbers, but we never really got into numbers for anything except for n, the principal quantum number. So what we're really doing is getting a little bit deeper than we got into with pre-AP chemistry. So the principal quantum number n describes the energy level on which the orbital resides. So the general energy level is the n value. The smaller n is, the closer you are to the nucleus. So electrons on the energy level 1 are closer on average to the nucleus than the electrons in energy level 2. So they're going to spend the majority of their life closer to the nucleus than would electrons at a higher principal quantum number, a higher n value, a higher energy level. So n represents our energy level. You remember this from last year? 1, 2, 3, 4, 5, 6, 7 were our energy levels. Now, the values of n are integers greater than or equal to 1. So 1, 2, 3, 4, 5, 6, 7. Now, this is basically the same thing as Bohr's n. So what Bohr talked about as energy orbits is our principal quantum number. They don't mean the exact same thing, however, but the terminology really does come out of Bohr's work. So Bohr's n was also dealing with energy level. Now, as n become larger, the atom becomes larger and the electron is farther away from the nucleus. So that's a fundamental relationship that you should understand. The higher the value for n, on average, the farther you are away from the nucleus. So you live farther away from the nucleus when your principal energy level is higher. Now, the second quantum number, and we're actually going to define this as a number. So there's the way in which you looked at it last year, and then the number it represents, because as quantum numbers, there are actually numbers that these things represent. Last year, the only one we gave a number to was n. Now, the second quantum number we're going to look at deals with the shape of the orbital. So in your head, think shape. Remember SPDF shapes from last year? That is really the angular momentum quantum number, which has the symbol of L. So the principal quantum number has a symbol of N. The angular momentum quantum number has the symbol of L. And remember, hereafter, I'm pretty much going to call this thing shape for the most part. So when we're talking about shape, there is an actual value of L that represents the different shapes we looked at. So this quantum number defines the shape of the orbital. Now, the values of L are going to be integers ranging from 0 to n minus 1. So this value for L is actually related to the value for n. So depending on what our value for n is, that has a role in what our value for n is, or for L is going to be. Now, if you look at our shapes, our S-shaped orbital, which remember was the spherical orbital from last year, has an L value of 0. So if we're talking about an S-shaped orbital, then it has the L value is 0. If we're talking about a p orbital, its L value is 1. A d orbital, its L value is 2. And the F orbital has an L value of 3. So just remember, 0, 1, 2, 3, SPDF. So if you remember your shape from last year, then you know the second quantum number. If you're in an S shape, it's 0. If you're in a P shape, the second quantum number would be 1. If you're in a D shape, the second quantum number would be 2. And if you're in an F-shaped orbital, the second quantum number would be a 3. Now, how is n related to L? Now remember, on the first energy level, all we had was the S. On the second energy level, we had an S and a P. On the third, we had an S, a P, and a D, if you recall from last year. So on the n equals 3 sublevel, we can have the, so if n equals 3, we plug this in here, 3 minus 1 is 2. So we're going to vary between 0 and 2. That's all it really says. That's our 0, that's our 1, that's our 2. So if n equals 4, we have 0, which is the S, 1, which is the P, 2, which is the D, and on the fourth level, we also have an F, which would be a quantum number for the second quantum number of 3. So that's the relationship of this. Fundamentally, the easiest way to think of this, our second quantum number is our shape. So SPDF 0, 1, 2, 3. Third quantum number is really called the magnetic quantum number, m sub L. So we have n, we have L, and we have m sub L. So for our third quantum number, we're really looking at this symbol m sub L. So we got L, we got n, and we got m sub L. Those are our three quantum numbers so far. Now m sub L is really about orientation. And you remember from last year, S orbitals are spherical. There's only one orientation. You can't spin an S orbital around its nucleus and occupy a new region of space. So there's only one orientation of an S orbital. But when we looked at p orbitals, let me color coordinate here and get the numbers right. There's only one orientation of an S. There is actually 3 different orientations of P, 5 different orientations of D, and 7 different orientations of F. So which of these orbitals we're actually in? Which orientation of P? Are we in the first P, the second P, or the third P? Well, there are numbers that actually stand for those 3 Ps. Last year we called it the PX, the PY, and the PZ because in 3-dimensional thought, that's an easy way to look at it. Those actually represent numbers, and that would be our orientation quantum number, the magnetic quantum number. Now, the values of m sub L are integers ranging from negative L to L. So once again, this new quantum number is related to the last one, just like the last one was related to the previous one. So the easiest way to look at this is the graph that I've shown here, because people look at this and they think this is something goofy. It's really not that big of a deal. If you are in an s orbital, you have an L value of 0. So that means negative 0, 0, well, it's just 0. That's all it is. So there's only one orientation of an s. But remember, if our L equals 1, then we're in a p orbital. And if you recall from last year, there's 3 different types of p orbitals. Well, the numbers we give them would be negative 1, 0, and negative 1. So if our L value is 1, negative 1, 2, 1 would be our range. So negative 1, 0, and 1. Integers from negative 1 up to 1, we're going to get 3. Now, did it need to be this complex? Not really, not in my opinion, but they ended up with ways that were mathematically related to each other so that they could express the relationship between n and L and m sub L. So, since we have 5 different orientations of D, and the L value for a D is 2, that means we've got negative 2, negative 1, 0, 1, and positive 2. So that gives us 5 different orientations. This would be the first D orbital. This would be the second, the third, the fourth, and the fifth. And then when we get to an F, there are 7 orientations, and the L value for an S, or for an F, I'm sorry, is 3. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. So all this does is gives us a way to describe the energy level, the shape, and the orientation with numbers. That's really all this comes down to, is we can use numbers to describe the same stuff that we looked at last year. So there's nothing new except for the fact that we're given goofy numbers and symbols to the exact same thing we talked about last year. Energy level, shape, and orientation would be N, L, and M sub L. And those things have numbers associated with it. These would be our L values, and these would be our possible M sub L values. Remember, each of these numbers represents a specific orientation of a specific shaped orbital. Now, s orbitals. Remember, s orbitals are our simplest type of orbital. They're spherical in shape, so it's a spherical region of space that these electrons would live in. Every energy level has an s orbital. So 1s has an s orbital. So the first energy level is an s-shaped orbital. The second energy level has an s-shaped orbital, and so on. Remember, when you're dealing with s orbitals, they can be on any energy level. So n can be any number greater than 0. The L value for an s orbital is 0. So L, remember, is talking about 0, 1, or 2, or 3. It's just another, it's a number instead of a symbol. So S has an L value of 0. Now, the M sub L value, well, remember, M sub L is orientation. There's only one orientation, and we're going to call that the 0 orientation. So remember, the M sub L is negative L to positive L. Well, if L is 0, that's all we got is the one orientation, the 0 orientation. So we have a 1 orientation. And remember, as n increases, the s orbital is going to get larger because as n increases, you're farther from the nucleus. So they're all spherically shaped, but when you go from the 1 to the 2 to the 3, you're getting farther from the nucleus. And remember, the 2s is inside the 3s, and the 1s is also inside because the center of all 3 of these is the nucleus. So they're all basically in the same region of space. And there are only 2 electrons that can live in this orbital 90% of the time. Now, there's also 2 electrons that can live in here because this is another orbital, and each orbital can hold up to 2 electrons, if you remember from last year. The electrons that are in this region of space can visit that region of space. They're just not going to live in there 90% of the time. 90% of their lives, they're going to be in a larger region of space. So remember, the electrons that are in the 1s are in regions of space actually inside the 2s and the 3s because the center of all of these is the nucleus. So this is just a bunch of electrons living in a bunch of different regions of space. The electrons that live in the 3s visit the 2s and the 1s. They're just not in those regions of space 90% of their lives. They're in that larger region of space 90% of their lives. Now, p orbitals and quantum numbers. Remember p's? The first time you can have a p orbital is on the second energy level. So there's no p orbital in the first energy level. So 2, 3, 4, 5, 6, 7, those are our p n values. Now remember, the L value of a p is 1. So L stands for what shape, and the p shape has an L value of 1. And the m sub L would then be -1 to +1. And that gives us 3 different orbitals. So this would be our -1, this would be our 0, and this would be our 1. So rather than saying px, py, pz, that's how we would say it this year. So all we're really doing is giving numbers to our different orbitals here. And we'll look at the periodic table and how this comes together in a second. Now, one goofy thing about p orbitals is people see this and they think 2 lobes. Remember, that's still just 1 orbital. So in this region of space, and this right here is probably the best physical way to look at this, in this region of space, in here and in there, 90% of the time, we're going to have up to 2 electrons living in that region of space. And the reason we have 3 different p orbitals is you can rotate the px, the py, and the pz and get a brand new region of space. So you have a new region of space where 2 electrons can live, and there's 3 different ways to orient that. So the 3 apartments, our px, our py, and a bz, are a -1, 0, and 1 apartment, because orbitals are apartments where electrons live. Now the d orbitals, the first time you see a d is on the 3rd energy level. So the 3rd, the 4th, and the 5th and beyond have d orbitals. Remember, the L value for a d is 2. And since m sub L is -L up to +L, we end up with -2, -1, 0, 1, and 2, 5 orientations of d orbitals. And you can see off to the left here what they look like. Don't really worry about the shapes. We don't really get that much into them. But remember, each of these goofy looking shapes is one region of space where up to 2 electrons can live 90% of their lives. And then finally, our f orbitals. The first time we see an f orbital is on the 4th energy level and above. The L value for an F is 3. So remember, what we're talking about here is the number for our F shape is 3. And since m sub L, the orientation, would be -L to +L, we've got -3, -2, -1, 0, 1, 2, and 3. 7 different orientations of an F orbital. And remember that each of these is a region of space where up to 2 electrons can live. So we've got 7 different orientations for F. So SPDF 1, 2, 3, 4, 1, 3, 5, 7. All those numbers should have meaning. The 1, 2, 3, 4 for SPDF reminds you of when is the first time you see that shape. And the 1, 3, 5, 7 is how many orientations each of those shapes have. And remember, this is represented by our L value. And which exact orientation we're in is represented by the m sub L value. Are we in the -1, the 0, or the +1 for our p's? So those are the first 3 quantum numbers, n, L, and m sub L. It's really dealing with a numerical address of where the electron is. Now, energies of orbitals, the next thing we get into here. And yes, I did say there are 4 quantum numbers. We'll come back to the 4th one in a little bit. For a 1 electron hydrogen atom, orbitals on the same energy level all have the same energy. So when you look at the hydrogen atom, and this is really why Bohr got confused, because to him it looked like if the electron was on the first level, it was this amount. If it was on the second level, regardless of where it was at, what we now call S and Ps, it was at that energy. And if it was on the third level, it was at that energy. When you have 1 electron, all of the energy sublevels, S, P, and D on the 3rd level, are all at the same energy. They're equal energy, which is known as degenerate. Degenerate means of the same energy. So when you have 1 electron, all of your 2nd level sublevels are at the same energy. All of your 3rd energy level sublevels are all at the same energy. They're degenerate. And that's why when Bohr was looking at his atom, it looked very simplistic. And the reason the mathematics went wrong in his model was when you have 1 more electron, the energy levels are no longer degenerate. The 2s and the 2p are no longer at the same energy when you have 2 electrons in an atom. Neither are the 3s's. The 3s, the 3p, and the 3d are all at different energies. So when you have 1 electron, the energy sublevels are degenerate. That means they're all at the same energy. So our S's, P's, and D's, and F's on a level would all be at the same energy. But when we get more than 1 electron, the repulsions that the electrons have for each other causes the electron energy levels and sublevels And really what we're looking at here is the sublevel. On the second energy level, what's going on with the S&P? You can see that they're no longer at the same energy, so they are no longer degenerate. And that's caused by the repulsions of the electrons. So in a many electron atom, orbitals of the same energy level are no longer degenerate. They're no longer at the same energy. And we need a way to really remember all of these different energy amounts since it's not as simplistic as Bohr thought. Now, before we get into that, which is really where we're going tomorrow, the next thing we're going to look at is our fourth quantum number. Now that we've got the idea of orbitals, levels, and sublevels, remember our level is n, our sublevel is which shape, S, P, D, or F. Which exact orientation we're in is our m sub L value. Well, you can have electrons that are in the same energy and on the same shape, an S, and in the same orientation. So the two electrons that existed in here would look like they have the exact same three quantum numbers. Now to review quickly quantum numbers, the two electrons we're looking at here that would be in our 2s. So if we're looking at something like lithium and beryllium, lithium has 3 electrons, beryllium has 4 electrons. So let's say with beryllium, the third and fourth electrons inside beryllium, they would both be in the 2s, so they would both have the same n value of 0, because, or I should say of 2, since we're on the second energy level here. I was getting a step ahead of myself. They would both have the same shape, so they're both in the same, they have the same L value. The S shape has an L value of 0, and they're both in the exact same orbital, so our M sub L would also be 0. So these two electrons have the exact same 3 quantum numbers. Well, we need to basically have a unique electron address, and both of these electrons can't be the exact same in there. And the reason they're different is the fourth quantum number, the spin quantum number. So that's one we're going to next, is the spin quantum number, which is n sub s. In the 1920s, it was discovered that two electrons in the same orbital don't have exactly the same energy because they're on the same 2s, so it looks like they're at the same energy, but they're actually not. One is at slightly higher energy than the other one, which makes sense because of the repulsive forces of putting two electrons in the same region of space. The second electron in there should be at a higher potential energy amount. So the spin of the electron describes the magnetic field that it generates, which affects the energy. So what we're really looking at here with the magnetic spin quantum number is the lower energy first electron in and the higher energy second electron in. They're going to have a different spin quantum number. The spin quantum number only has two allowed values. You can be a positive 1/2 or a negative 1/2. So the first electron in our 2s orbital would be our positive 1/2 spin. Our second electron in has to be at the negative 1/2 spin, representing the slightly higher energy state in that 2s orbital. So when we were looking at our electrons inside our atom here, the first one would have an m sub s of positive 1/2. So that would be its four set of quantum numbers. But that fourth electron has to be the negative spin one, which is why I showed it as a down arrow. So its four quantum numbers would be 2, 0, 0, negative 1/2. And therefore, the four electrons inside that exact orbital do have a unique set of 4 quantum numbers. So the magnetic spin quantum number is really what gives us a unique set of quantum numbers for any given electron in any given orbital. So no two electrons in the same atom can have exactly the same energy, can have exactly the same 4 set of quantum numbers. So really, you can't have the same set for any two electrons in any atom. And that's what's known as the Pauli exclusion principle. So the Pauli exclusion principle is basically each electron is at a unique energy, which fundamentally means each electron has a unique set of 4 quantum numbers. And that ends our second set of notes from chapter 6.